Hello everyone. So now we'll see some properties of convergence in Rth mean. Let us first recall the definition of convergence in Rth mean. So we say that xn converges to x in Rth mean if expectation of mod xn minus x raised to r converges to 0. Sequence of expectation is a sequence of real numbers. So if it converges to 0, then we say that xn converges to x in Rth mean. And this can happen for any r positive. Okay, if it happens for one r, it doesn't necessarily hold true for other r. Okay, now first we'll try to see if xn converges to say two different random variables in Rth mean, are they equal almost surely. We saw that in almost sure convergence this happens, in probability convergence also this happens. However, in convergence in law it doesn't happen. We have already seen it. So now suppose xn converges in Rth mean to x and xn converges in Rth mean to another random variable y, then we have to check whether x is equal to y almost surely. Okay. Now we are going to use the inequalities, moment inequalities to prove this. So we have CR inequality. CR inequality says that if I have two random variables x and y, then I can try to do some modifications about their expectation. So first what I'll do is, because I know that xn is converging to both of these, I will bring in xn. So this will become x minus xn plus xn minus y whole raised to r. And now CR inequality can let me separate these two expectations. So it says that this is less than or equal to CR expectation of mod xn minus x raised to r, okay, plus expectation of mod xn minus y raised to r, okay, where CR is a constant. We know that for a fixed r it's a fixed constant. So we know that xn converges to x in Rth mean and xn converges to y in Rth mean. So this goes to 0, this goes to 0 as n goes to infinity for that particular r. Hence we have 0 less than or equal to expectation of mod x minus y raised to r less than or equal to 0, because expectation of modulus cannot be negative and hence this must be 0. Now can this be used to conclude that x is equal to y? Let us try to see. What I'll do is, this expectation of x minus y raised to r, I will split as r by 2 and then square. Okay, so this we know is equal to 0. Now let this quantity be called as z. Okay, so what my z is? My z is mod x minus y raised to r by 2. So what I have now is expectation of z square is equal to 0. Now the expectation of z square is 0, then we know variance of z is expected z square minus expected z whole square. So variance of z is always less than or equal to expected z square. Hence variance must also be 0, because variance cannot be negative and expectation of z square is 0. Okay. And if variance is 0 and expectation of z square is 0, then this third term will also be 0. So what I have is expectation of z is 0 and variance of z is 0. This means z is degenerate at 0. So z is degenerate at 0 means mod of x minus y raised to r by 2 is equal to 0 almost surely. Hence we get x is equal to y almost surely. Okay. So the rth mean limit is also unique almost surely. That is, if I have a sequence of random variables converging to two different random variables in rth mean, then those two random variables must be equal almost surely. Okay. Now let us try to see one example of rth mean convergence. So we will start with a discrete random variable. So let xn be such that xn takes value 1 by n with probability 1 minus 1 by n square. Okay. And it takes value n with remaining probability, that is 1 by n square. So xn takes only two values, n and 1 by n. Now what can I say about convergence? What do you expect? Intuitively looking at xn, what do you expect? See, the probability of xn taking high value, that is n, is very low and it is going to 0. On the other hand, probability of xn going near to 0 is quite high and that probability is going to 1. So we expect that xn probably goes to 0 in at least say first mean. So if I want to check that, I have to check expectation of xn minus 0 raised to 1. What happens to this? So let us try to see if we can compute it. So expectation of mod xn, anyway xn takes only positive values, so this is same as expectation of xn. Expectation of xn would be 1 by n into 1 minus 1 by n square plus n into 1 by n square. So this is 1 by n, 1 minus 1 by n square plus 1 by n, and we can see that both these terms converge to 0. Okay, first term also converges to 0, second term also converges to 0, hence this converges to 0. Therefore I can say xn converges to 0 in first mean. Okay, first mean. What happens in quadratic mean? That is, what happens if I consider expectation of xn minus 0 whole square? So this would become expectation of xn square. Xn square would mean 1 by n square into corresponding probability 1 minus 1 by n square plus n square into corresponding probability 1 by n square. Okay. And now this first term will go to 0, no problem. Okay, first term will still go to 0. However, second term is now going to 1. Actually, it is equal to 1. So what I have is expectation of mod xn minus x whole square goes to 1. Therefore, xn does not converge to x in quadratic mean. So we have an example where I have first mean convergence but second mean convergence doesn't happen. That's what I was saying while writing the definition. If it converges for some r, that doesn't necessarily mean it converges for every other r. Okay. But can we at least say for some other r? Yes, there is an interesting result. So if xn converges to x in rth mean, then xn converges to x in sth mean for every s which is less than r. Okay. So if xn converges to x in quadratic mean, then xn would converge to x in first mean also. However, the reverse is not true. So if the convergence happens for higher order moment, then it automatically holds true for lower order moments also. Okay. Let us see another important result. When does convergence in quadratic mean happen? Can we have some checking criterion? Okay, we had some criterion for probability convergence, almost sure convergence. So can we have something similar for quadratic mean convergence? So suppose xn is a sequence of random variables, then xn converges in quadratic mean to a degenerate random variable, that is a constant b, if and only if expectation xn converges to b and variance xn converges to 0. and it's if and only if, means the condition is necessary as well as sufficient. Okay, the proof is quite easy. You can try to write down the proof. Okay. Now we are using rth moment of mod of xn minus x while defining convergence. So does it mean that moments also converge? So yes, there is a result which says that if xn converges to x in rth mean, then expectation of mod xn raised to r converges to expectation of mod x raised to r. Okay. So if xn converges to x in rth mean, then the expectation of mod xn raised to r converges to expectation of mod x raised to r. However, the reverse result is not true. Means if we have convergence of moments, that does not necessarily mean convergence in corresponding mean. Okay. So convergence of rth moment does not imply convergence in rth mean. Let us see one example to check this. So suppose xn is an indicator variable. So xn is indicator of some set A. So basically my random variable is free from n. Okay. For some A which is subset of omega such that probability of A is half. Okay, probability of A is half. So xn is defined as this, and let me define x as indicator of A complement. But probability of A complement is also going to be half. Okay. Now let us try to compute the expectations. So expectation of mod x raised to r would be what? X takes only two possible values, 0 and 1, and 0 with probability half and 1 with probability half. So it is 1 raised to r into half, correct? Similarly, xn also takes only two values, 0 and 1. So this is also 1 raised to r into half, that is half. Therefore, expectation of mod xn raised to r converges to expectation of mod x raised to r. In fact, not just converges, it is actually equal. Okay. However, now if I try to compute expectation of mod of xn minus x raised to r, then what do we get? So mod of xn minus x, we know that xn is an indicator function of A and x is an indicator function of A complement. As a result, they will never be equal. The difference will be either plus 1 or minus 1. So this will always be 1, right? In modulus, this will always be 1. So expectation of mod xn minus x raised to r will always be 1, and hence it cannot go to 0. Okay. Therefore, even though expectation of mod xn raised to r converges to expected mod x raised to r, xn does not converge to x in rth mean. Okay. So what are we concluding? That convergence in moment does not imply convergence in rth mean. Reverse is true. However, this way the result does not hold. Okay. So let us stop here.